Today we will be talking about simultaneous fitting of plasma and urine data. And that's a little bit different from the topic that we suggested or that we had on our original schedule. But we said we would be carefully listening to your feedback, and that's what we did here. So we received numerous feedback around plasma and urine data, and that made us that's why we have decided to change the exercise for this lesson. The original focus was on a simultaneous fitting of IV and PO data. But we've looked into the book, the Gabrielson and Weiner book, and found an exercise where actually there is one exercise PK6 where you do simultaneous fitting of IV and PO as well as plasma and urine data. So we picked that for this exercise, and that's what we gonna show today. As usual, I mean, we've got the Q&A panel on the right-hand side of the Cisco console. So whenever you have a question, just enter them there, and we will get back to that at the end of the session of the demo, and respond to that then during the Q&A session. So let's move on. So as I said, I mean, we want to fit plasma and urine data, but the first step, I mean, I've divided this up into two steps. First, we fit IV and PO data in one single step, and then add the urine data to it and do a complete fit then. So we want to find estimates for a bunch of parameters like clearance, volume of distribution, bioavailability, the absorption rate constant, lag time, and the fraction excreted. The data that we are using here is typical from one subject, single subject. This subject received an oral dose of 25 mg, and this was followed by an IV dose of 12.5 mg. And following the doses, plasma and urine samples were collected. Okay. First of all, a look at the data, the exploratory data analysis. So we are seeing here the semi-log plot of concentration and amount excreted versus time. You see there are four curves. The small ones or short ones at the top, these are the amount excreted for the two collection intervals from 0 to 24 hours and 24 to 48 hours. And below that are the two plasma concentration time curves. And what you can see, there's a single slope that you can see here. So we would expect that a one compartment model would fit the data very well. So how do we build up the models? The model, first of all, as I said, we start with fitting of the IV and PO data. And you see here that the population box is checked on from the built-in on the top left-hand side. Let me see, I can add a laser pointer. So the population box needs to be checked on, and this is because you've got two different inputs, one from IV and one PO, and you want to do the fitting together. So that you end up with one value for clearance and volume. It's a PK type, and most of the stuff is much as default. Parameterization, we stick with clearance. For absorption, we choose extravascular, and we expect a slight delay between dosing and first measured concentration. So we check this box T-lag. We'll stick with one compartment. That's what we've seen from the exploratory data analysis. And that's the rest remains as default. So the next step would be to go into the graphical model builder, where we need to add the bioavailability to the extravascular dose point. We just want to have this estimated as well. And then what we also need to do is we need to add another dose point for the in vitro data. With that, you've built up the model. You can fit the IV and PO data and get your first set of estimates. So once this model is completed, you can then switch to the second one, where you just need to add a continuous observation, and this is our amount excreted, observed, AEOBS, in this field that you link to the elimination compartment. And for the elimination compartment, you can switch on the function to estimate the fraction excreted. So overall, we only use the built-in options and the graphical model builder. But since we are at the PML school, we just need to look at the code as well. So here's the textual model. It's just taken directly from the graphical model builder, and it's just a different representation. So for the structural part, we've got 3 differential equations for the individual compartments, for the plasma compartment, absorption, and elimination compartment. And you see here this urine compartment, this allows you to also switch on the function to estimate the fraction excreted. The next line shows you that converts the amounts to concentrations. That's typical. And then we have the 2 dose points. The first one, the IV input. The second one is the oral input. And here we've switched on 2 functions, the T-lag, the lag time with parameter T-lag, and the bioavailability with parameter F. These gets estimated. Next part is a residual error model structure. So we've got estimated standard deviation for the residual error for the concentration and the amount excreted. And we use in both cases an additive residual error model. As you can see here, the concentration plus CEPS and the A0, the amount, plus the error model. Then there are the structural parameters. This is typical for the population model build-up. So this is just useful to show in order to be, become more familiar with this notion and the language. Typically, you have in a population model next to the fixed effect, which is denoted as typical value, TV, volume, for example, you have some random effects, but since we only have 1 subject, no population data, we don't go this road, so we are just having the fixed effects for each structural parameter, like volume, fraction excreted, clearance, and so forth. And the fixed effects are specified in this with this statement, with a fixed F statement, where you just have a vector represented with 3 figures: the lower bound, the initial estimate, and the upper bound. So this is then done for each of the individual fixed effects. So this is the final model. So in order to get started, we need to get some ideas for initial estimates. This is a 1-compartment model, so what we can do is we can run an NCA to get volume and clearance from the NCA. For the bioavailability, we just take the AUC-PO divided by AUC-IV, the dose normalized AUC values. Typically, we start the absorption rate constant with a value of 1. And for T-lag, we take the first measurable concentration after the dose. Fraction excreted, this you can get from an NCA on the urine data, and that is just the percentage recovered divided by 100. Okay, and now let's start the demo. I'll just share my Phoenix. Okay. So here we've got my project, and this is the data. We've got plasma data, just for the 2 routes, IV and oral, time points and plasma concentrations. And we've got a few urine measurements, amount excreted and the volume. And in this way, for this exercise, we actually need two different dose tables, and I tell you why. So this is a dose table for the NCA, where you got the dose amounts in one column, and then you've got another one for the Phoenix model, where you've got the dose amounts in two separate columns. So maybe we start by joining these two spreadsheets together. So we just send this to a data join worksheets object, and I'll just put it into the demo workflow. And here for this plasma worksheet, we have a sort variable, so that should match between the two worksheets, that's route and time, and we include the source column. For worksheet 2, we take the plasma and urine. Here again, we take this as sort, route, and time, and include amount excreted and volume. And if you run this, you have a data sheet like this. Now, when we want to run urine NCA, we need a few additional columns, and this is typically done through a data wizard object. So I send the output, the results, to a data wizard object. And here it asks you for an action, and you can choose between those three actions. In the first step, we want to change the units. So we add a properties step where we convert the volume a unit from milliliters to liters, and we just want to convert this. Okay. Then we need some additional parameters for urine NCA, so we'd add a transformation step, a custom one, where we just want to have the start time of the collection interval. And that is actually we only need that for those records which have an amount excreted. So we take an if clause. If the amount excreted is larger than 0, we say this is time minus 24. Otherwise, we don't want to give it any value. Okay. This is for the start time. Then we need another transformation, and that is actually division x by y. That is a conc urine. And we just divide the amount excreted by the volume. And that's it. If we run this, we have amount excreted, volume, the start time, and the conc urine. Now let's first plot the data. So we just use a XY plot object. So we have time, we group by route, the plasma concentration, and the amount excreted. And that's what we see, that's the plot. We may use some log scale. And this is the data that we have also shown on the slide. So this looks correct. Now let's start with an NCA. So we take the result from the data wizard. We send this to an NCA object. In this case, we call this maybe NCA plasma. So we have we sort by route. We have the time and the concentration. Next, we need the dosing, and this is actually this one, the first dosing table, where we've got the dose and the time of dose. In this case, we have two different dosing options, IV and PO, so the dose type needs to be specified, and that's part of the worksheet, dose type IV bolus and extravascular. That's it, so we just give it a go. There was one. sort root here. Okay, and here are the results from the NCA. So you can look at volume and prediction. So the volume is around 300 and clearance is around 5 to 6. These are the values that we need for our Phoenix model. We just copy this and paste it back to the workflow. And this will be our NCA urine data. And here we need to change the model type to urine. And this asks now for the start time and the end time. So the end time was time, and the start time we've calculated. The concentration of the urine was this one, and the volume was volume. Right. So, and the dosing was the same, so we can execute that. And here we have the percent recovered, which is 7%. So maybe taken 0.1 for fraction excreted. So this is now everything we need for the initial estimates. So we can now start to model the data. So we go back to the data wizard result where we got all the observations included. We send this to a Phoenix model object. And this is our IV and PO model. So as I said, we'll stick to the population box. We've got PK, and typically we don't go with a closed form. We use differential equations. We change absorption to extravascular and check on the box with TLAC. Let this be calculated. And we stick with one compartment. So now we need to do the mapping. The route is the ID, time is time, and CP is our observed concentration. So this is for the extravascular part. Now we need to go to the graphical model builder, where we have here the absorption compartment, which gives us a few other options, like, for example, this is the bioavailability checkbox, and here we can just enter F as a parameter. And for this, we also need to insert into the model a parameter that we call actually F, so that this parameter is specified. That's this. Now we need another dose point. We have right now only the extravascular dose point. We go to the central compartment and we just add another dose point, which is A1. That's it. Now we need some, this is all the model building part. Now we can move to the dosing. And this was dose number 2, where we have the root as ID. A1 is A1, AA, these are the amounts for IV and PO, and the time is time. So this is now set up properly. We now need to enter our initial estimates. We've got times up to 150. The volume we said was 300. The clearance was around 6. T-lag was something like 0.2. Ka was 1, and F around 1. Can I use an overlay? So you see in an overlay you see the IV and the PO data. That should be good enough. So we can take those, copy them to the initial estimates tab, to the fixed parameters tab, and run options. We change to naive put, because that's what we want to do here. and execute the model. Okay, and then we'll get the theta values here for volume, clearance, T-lag, Ka, and F with standard errors calculated. So have a look at some of the plots, like this one. Just look at the logarithmic scale, and you see these are the fits. And this looks quite good. So this is fitting simultaneously IV and PO data. Now we want to also add the urine data, so we copy this model and paste it back to the workflow. We just call it plasma urine IVPO model. We need to go back to the model here, and here we need to add another observation, the amount excreted, and that is a continuous observation. Obviously we have the same name, so we need to change that. And we also need to change the input. That's this. And for the elimination compartment, we can check the box that you want to calculate the fraction excreted. That's it. So this is just when you want to fit simultaneously plasma data and urine data. Now we need to go back to the mapping, and here you see AE ops needs to be mapped, and that is our amount excreted that we've got from our input data. We can have a look at the initial estimates, and for FE we said it was something about 0.1 fraction excreted, and the rest should be okay. Here you can also see AE versus time. We let the initial estimates be like what we've got here, and a run option is naive pooled, and we can execute. Okay. Here again, our final estimates for volume, fraction excreted, clearance, and so forth. And now let's have a look at the fits. These are our fits, the amount excreted, and the observed concentrations. So there are lots of diagnostic plots here. Most of them are only useful for, you see the name POP, for population modeling. Although we've did this here, we don't have any random effects, so some of the stuff has not been calculated. What you can see here is, for example, the individually weighted residuals versus individual predictions. We can just do an auto-scale best. And we see here some fan-like structure, like in this case. This doesn't look very good because the residuals for smaller predictive values are smaller than for higher ones, so we might want to change the residual error model structure, and that's what we could do here. We can just copy and paste this model once again, and we call this multiplicative. And here we just need to change the observation here from additive to multiplicative. This is now a percentage of the residual error, and we just give it maybe 0.3, 30%. And we can run the fit once again. Let's see. We got the fits. Okay. I mean, the fits were already optimal, rather optimal, but let's see at the diagnostic plot. Here you see now, you see a better spread of the residuals, individual weighted residuals, so this looks much nicer. With that, I guess I'm at the end of the demo session, so let me stop sharing this and go back to the slides. So this is the end result. What we've seen is we build up the model in 2 stages. First, we've just focused on IV and PO data, and then we've just added the urine data with the amount excreted that we fit, and we found some very sharp estimates for all the parameters. Now, what we did here, we had a typical 1-compartment system and fit the data, and I showed you how to derive some initial estimates from NCA for both plasma and urine, and we went through the code in PML, and you saw how we can fit the model to the data, and we've looked at the results. With that, I guess I'm at the end, so we can start the Q&A session, so I'll hand over to Chris to give us the questions.
Yeah, so everyone, this is an opportunity to ask on the Q&A tab. So we do encourage you over the next few minutes to type in your questions. Bernd, for now, maybe we can talk a little bit about units. That was one of the first questions that came in. And so can you talk about keeping similar units between concentration and dose, and also why we want to have a dosing sheet that contains units?
Yes, that's right. Yeah, that's a good one. So what you see here, we started with units right from the top. So we've got micrograms per liter. That's our plasma concentration. And for urine, we had amount excretion created in micrograms and the volume in milliliter. So you see the difference here in the units. This is the volume unit in liters and milliliters. This has to be corrected, so we need to change this here in order to be really consistent, because there are no unit conversions being done when you are in the Phoenix model. There are some unit conversions done in NCA, for example, when you enter milligrams data and you've got concentration mass units of micrograms. NCA will take care about those differences, but not the Phoenix model. So whatever you start with should be consistent. You should always use the same mass units. Or if you switch to molar, you always need to use the same molar units. And that's what we are trying to go through here as well. So we had a dose of micrograms. That's as a micro as a mass unit here as well. And the plasma concentration was also the same. So you see, you need to be consistent, because the Phoenix model simply doesn't care about a unit conversion. So you need to make sure that when you look at the final theta sheet, that the units are correct. Like, for example, the estimate for the volume is in liters. And for clearance, these are liters per hour. And you want to be, you want to have this output. And you have to do some work in it before going into the Phoenix model in order to really make sure the units are correct. Okay?
Yeah, thanks, Bernd. The next question has to do with the selections on the Run Options tab. And so the reason that we're using population and why are we using naive pooled. So can you give a little more detail about that?
Yes, I mean, naive pooled, this is maybe a license question. I mean, you could also use some other engines like available here, like FOCE or QRPEM. But since we are dealing with Phoenix Win on Lin, the license will only give you access to naive pooled method. And that's fine for our purposes. We just have two different inputs, IV and PO data. And for this exercise, this is the right method to choose. But maybe Dan, you may have some additional comments if you want to chime in.
Yeah, sure. So Bernd, as you correctly pointed out, the Wendt non-lin license does support naive pool, which is what you'd want to use in a situation like this where you have a single subject. If you're doing population modeling where you're fitting large numbers of subjects simultaneously, then you could use Wendt non-lin to fit each subject separately. But if you wanted to do a combined fit, as you pointed out, you would need an NLME license to do the full extended least squares or maximum likelihood fit.
All right. Thanks, Dan.
Thanks, Dan. So we have a couple more questions, Bernd. The first one is to go over adding the second dose point to the central compartment.
Yeah. This is just you pick the central compartment, and then you have here the choice between 0 dose points or 1 or 2 or split.
Yeah, so this is one of the really handy features of the graphical mode, having the simple interface to add dose points and so on. And then the follow-up question was, could you please go over the model in textual mode?
Yes. All right. Yeah. True. I mean, this is something I've shown in the slides, but let's do this one, and I'll copy this one and paste it. And then we just, this is just a copy, so we can now add it as textual. And then you see the code here. This is the code. Okay, this is the 3 differential equations that we've seen here. We've got an annotated version of this in the slide deck, and this will also be posted later on to the forum. So these are the 3 compartments, and with their differential equations. We've got here the conversion to concentrations. Here are the 2 dose points. These are just standard parameters that are added to this intravascular dose point. And the same you see also for the extravascular dose point. What is important for us are these 2 parameters. These are has been explicitly checked on. So the lag time and the bioavailability will be calculated if these are checked on. Then we've got the 4 lines about the residual error model. I mean, here you've got lots of options. Maybe something to point out here is you could have chosen the same error for the amount excreted as for the plasma concentration. I've chosen to divide this up into 2 different error terms. You can do that, and you can also change the residual error model structure. For example, you can change the plasma concentration model from additive to multiplicative and vice versa, and do the same or something different with the amount excreted. So you've got lots of options here to pick from. Whatever is best suited for your data set, you will find out, and it's really easy to switch between those options. Then we've got the structural parameters. Here now you see that there's an additive term with the exponential function with NV. This is just the standard code for a population model. And this is just used because I've checked on population mode and I switched to textual mode. So you can eliminate these parts because we don't have any random effects since we don't have population data available. So this is just a way to account for the 2 different sources of variability, the fixed effects and the random effects. And this is done for each of the structural parameters. And then you specify the fixed effects. This is, where you give the lower and upper boundaries, and also in the middle the initial estimates, what you can see here. And that is a typical syntax for that. And for the random effects, okay, these have been included since we've got population box checked on. But this is how it looks like in textual mode. I hope that's
so Bernd, there's a couple of questions about the error model for the urine, and we have the red error message, so maybe just describing how to add like an AE epsilon.
Yes, that's right. That's true. Yeah, I've seen this warning. You want to change this to AE eps. Yeah. And then, wait a second. Maybe that is something better. You can leave that on, or you can, as I did here, for example, in my last model. When you look at the model text here, I don't want to change it, but you see it here. So you've got AE ops is a multiplicative additive residual error, whereas the plasma concentration we have a multiplicative C times 1 plus C eps. And here we've got given some initial estimates for the standard deviation. The same. Oh yeah, this is actually C eps. This is wrong. We need to actually change this to AE eps. Yeah. Okay, this one a small error, but this is easily being fixed by going into the structural model and just changing this here, for example, to AE EPS. Okay. But as I said, there's lots of flexibility around this, and you need to work out on your own data set, I mean, what would be the best structure for that. Okay.
Yeah. So we had one other question while we're on the error model topic. So the initial value for the multiplicative was 0.3. Maybe we can invite yourself or Dan to comment on that question. An initial value for a multiplicative error model.
Yeah, I mean, maybe Dan, you can you take this question, please?
Sure. When you're fitting an additive error model, the standard deviation has the same units as your original data. So generally, a value of 1 will converge, but if your data is quite large in magnitude, you may need to increase the 1 to be 10 or 100 or something comparable to the actual range of your observed data. When you're fitting a multiplicative error model, then the standard deviation is a % CV. So there, generally, it's good to use something like a 0.1 or a 0.2 or a 0.3%, which would translate to a within subject error of about 10, 20, or 30%.
Okay, thanks, Dan.
Okay, so we've answered a spread of the questions, and if we didn't get to your question, there will be a follow-up posting on the forum to respond to all questions.
All right, yeah. Thanks everyone for attending. So we're closing the session for today. One announcement, in 2 weeks' time, we will have our next session. Dan Weiner will be presenting the TMDD models, various approaches to model this kind of data, and we're looking forward to this session. And if you haven't registered yet, I mean, please do so, and we'll pick up from there. And we'll in the next day, over the next day or week, we will present you with our new schedule. We have prepared a schedule for 2017. So we've got 14 sessions to go in 2017. So I'll send out a note to everyone so that you have an overview and pick exercises that you are interested in. With that, I guess I'm at the end. I'm thanking you for your attention, and Dan and Chris for helping me on the session, and hope to meet you next time in 2 weeks. Thank you.